We are a consortium of Earth observation specialists working for the European Space Agency.
The framework in which we operate is twofold. The first guiding principle is the United Nations Sustainable Development Goal 11. Make cities and human settlements inclusive, safe, resilient and sustainable. The second framework is the Project Implementation Strategy in international financing institutions like the World Bank and other development banks.
Our aim is to extend and improve the use of satellite data for the monitoring of indicators in order to reach Sustainable Development Goal number 11. We also want to facilitate international development work in a globally consistent manner by using Earth observation data and methods.
We have covered 32 cities around the globe with a total of more than 510 products and 11,000 square kilometers mapped. Our basic products comprise status and evolution of urban extent, as well as land use and land cover and its change over time. More specifically, targeted maps include slum maps, maps of open and green spaces, building footprints and heights, infrastructure, as well as hazard and risk maps. Based on these maps, we generate spatial analytics and the before-mentioned indicators for SDG 11.
These tools are very much relevant because they provide evidence.
In general, the preparations of bank operations take several years, but in these cases, it only took around 6 to 8 months for the preparation, thanks to the whole analytics, maps, and data evidences. The best part is that it was helpful to communicate with various stakeholders on the ground.
The two speakers today, they both coming from GAF. This is first Daniela Angelova. She's a remote sensing expert for urban planning. And the second one will be Amelie Broszeit, who is a technical expert in remote sensing.
Thank you, Manuela, for the great introduction. Hello, everyone from all different parts and corners of the world. So, as Manuela already mentioned, my name is Daniela Angelova, and on behalf of GAF Germany and all partners involved in this project, I would like to thank you all for your participation today. And we hope that with our webinar today, we'll spark and light up your interest in geospatial technologies and its application for urban topics. And we hope also that we will be able to answer some of your questions. Before starting, I just would like to mention that the webinar today will present some of the major challenges in urban development and planning in developing countries, and the potential for the application of geospatial data to improve assessment of urban growth and planning. These issues will be illustrated with various examples from the Earth Observation for Sustainable Development Urban portfolio and different use cases. To start with, I would like to point your attention first on the European Space Agency and activities. So ESA is an international intergovernmental organization with 22 member states and also cooperating states, including Canada. The purpose of the European Space Agency is to provide and to promote cooperation among European states in space research and technology, and of course also their space applications. It's important to note and to mention that ESA is one of the few space agencies in the world which is combining responsibility in nearly all areas of space activity. What does this mean? That, of course, on one hand, ESA is covering the space science and also human spaceflight, exploration, launchers, and navigation. Earth observation, which this project is part of, operations, technology, and last but not least, telecommunications. On the next slide, you can see the European Space Agency collaboration with international financial institutions in the domain of Earth observation. So for the last 10 years, since 2008, there are 65 small-scale demonstrations of Earth observation-based environmental information, which are supporting multilateral bank development projects. The aim, and so the main goal of those small-scale demonstrations is to respond to specific geospatial information needs. In order to do so, there are a lot of memorandum of understandings and secondments in place with the World Bank and specifically an Asian Development Bank. And as you can see on the map, those are actually the locations where ESA is currently operating with those small-scale demonstrations. If you would like to receive more information on the activities and applications of the European Space Agency in different domains, we provided you with a link to the different reports which are available and documents, so that you can further dive deeper into the area which you're interested in. Next, I would like to present to you the project background and to tell you a bit more about the project. So, as I already mentioned, the project is Earth Observation for Sustainable Development in the Urban Domain, and it was initiated in May 2016. And of course, as I already mentioned, it's financially supported by the European Space Agency. What are the objectives of the project? First, with this project, we would like to improve understanding of Earth observation applications for urban development, specifically with the multilateral development banks and developing countries. On the other hand, we are trying to mainstream Earth observation applications in an operational manner into development programs. The project itself is implemented by a consortium of European Earth observation service providers, and it's led by GAF AG here in Germany. And down on the slide, you can see all the partners which are involved within the project, and they're all, as I already mentioned, European EU service providers. Let's start. I would like to tell you a bit more why urban growth is so important, especially in developing countries, and the assessment of this urban growth. There is a forecast that by 2050, around 66% of the global population, or 2.5 billion people, will be living in the urban areas. This means that 90% of the world's urban population growth will occur in cities in Africa and in Asia. You can imagine that those two continents, Africa and Asia, they're the most vulnerable in terms of providing with proper infrastructure and for better living standards of the citizens. The urban growth itself poses a lot of challenges to the governments, especially in developing countries, which are trying to manage this staggering growth in multifaceted environments. So some of the challenges are infrastructure, access to clean water, electricity, sanitation, basic services in order to avoid urban poverty. It's very important to mention that all those issues and all those challenges have been already embedded in several of the United Nations Sustainable Development Goals, which have been established in 2015. Therefore, the ESA EU4SD project aims at addressing all those challenges by using Earth observation data and respectively their EU-based solutions. To start with, I would like to present to you a general overview of the project portfolio and the Earth observation products for urban development, which we have developed and produced, and we are able to do in the future as well. So to start with is a baseline, let's call it a baseline product of land use land cover classification, which includes urban and peri-urban areas. And having this land use land cover product, we are able to extract and to monitor green areas and networks on one hand, then also to analyze the extent, imperviousness, and change of the urban growth itself. We also have the capacity and knowledge to generate building footprints, also population density, which provides with a proxy of the population estimate in a specific city. Waste sites, which is also an interesting product for local governments in developing countries. We can provide with transport infrastructure and informal settlement products. And last but not least are the so-called risk products, which include flood risk, landslide, and terrain motion, which are very interesting and very important for local governments in developing countries in order to fight and to tackle with the challenges from urban growth. In the next slide, I will present to you the Earth observation-based solutions for urban planning, which we can provide with our products. So on one hand, we are able to analyze the effectiveness of urban master plans and also to monitor urban growth and analyze what is the extent of urban growth throughout the years. Then we can also provide recommendations for infrastructure planning, which will be based on road network analysis and accessibility analysis. And we can also assess and monitor slum areas and informal settlements, which is actually based on a robust methodology, which we have developed in our project. Then we can also provide with solutions for urban green areas planning. And as I already mentioned, a proxy of population distribution and density estimations. Building heights, it's another EU-based solution for urban planning, which we have been working on last year here at GAF. And this case was specifically for focus on tax estimation. So the local government used our building heights in order to estimate the taxes in the city and to propose future updates, let's say. And as I already mentioned, we can provide with recommendations in terms of risk and disaster assessment by mapping floods and land subsidence monitoring. And of course, all those solutions and products, they have been all focused on monitoring the urban indicators within the SDG goal 11. Therefore, our end users are local authorities, ministries. They can be also engineering firms and international donors like the World Bank, Asian Development Bank. And last but not least are also the United Nations agencies like UN Habitat, UNDP, and various NGOs. With the next slides, we would like to present to you a specific use cases from those products which we have developed in the last year. So I will start with the first example, which is a land use land cover mapping in Arusha. Arusha is a city in Tanzania. So you see so this is a very high resolution image from QuickBird for 2005 of a specific extent of the city. And this is the classification which we produced, a land use land cover classification, including 29 different classes. So the most predominant class is with the yellow color, which is agriculture. So why we selected to show you this specific example? Because you can see in the next slide how this specific area changed only for a period of 10 years. So this is the land use land cover classification for Arusha in 2015. So you can see the drastic expansion of residential areas and conversion of agricultural areas at the expenses of residential areas. So this is just the first example of our product portfolio. And then we are, of course, able to do land use land cover change mapping. So on this map, you can see our two areas of interest. So the black line represents the core urban area, and then the red one is the peri-urban area. So all those 29 classes, which you saw in the previous slide, we combined them, we categorize them in 4 different classes, which are namely urban densification, which is presented in blue color. Then we have urban residential extension, which is shown in red color. Other urban land use extension is with pink. And last but not least is the change within natural and semi-natural areas in green color. So let me tell you a bit more what those classes actually mean. So urban densification with the blue color represents actually an increase in the soil ceiling of a residential class. So in other words, in 2005, we had a residential area which was sparsely distributed around. And for a period of 10 years, this area was very much densified and a lot of new buildings popped up for a period of 10 years. So this is what is the definition behind the urban densification category. The urban residential extension, I would say it's a rather straightforward class to understand. So, for instance, we had agricultural area in 2005, which has been converted to residential area until 2015. Other urban land use extension, this class can be, I would like to give you an example that, for instance, in 2005, the specific area was classified, was not only classified, but it was truly urban park, let's say, within the core urban area of the city. And let's say the local government decided that this urban park will be converted to industrial or commercial area. And the last class is the changes within the natural and semi-natural areas, which means that at the beginning of the study period, the area was forest, and then in 10 years, it was converted to agriculture. You see basic statistics which we can produce. We generated statistics for the overall area, combining core and peri-urban, and of course, only for core and peri-urban specifically. There are some interesting trends in the specific case of Arusha. For instance, in the overall area, we see that the most predominant class is urban densification with 48%, whereas in the core urban area, it experienced more urban residential extension. So those are also part of the, let's say, some preliminary conclusions that residential extension is more dominant in the core urban zone, and whereas residential densification is more dominant in the peri-urban zone, as you can also observe on the map with the red color urban extension and blue color urban densification. Let's move further. I already mentioned to you that we are able to produce the urban extent and to monitor the urban growth throughout the years. This study has been done by one of our partners, namely the German Aerospace Center, DLR, here in Munich area. So this map represents the urban extent of Arusha in the year 2000. And this is a binary mask of the urban extent, which includes two classes, as you can imagine from the term binary. So we have the white class represent the build-up area, and the black color is all other types of land uses which we were not interested in this specific study of the urban extent. So this is the urban extent in 2000, and you can see how it developed throughout the year. So this is 2005, 2010, and 2015. So I'll just go back to show you again, starting from 2000, the urban extent, and then how the city is growing throughout the years. Based on the urban extent, we were also able to generate imperviousness layer, which is providing the degree of soil sealing from 5 to 100%. In other words, this means that we were able to measure what was the degree of imperviousness of within the urban extent of Arusha. The darker the color is, the higher the degree of imperviousness on the map. So this is the result for 2000, and then we see respectively for the next three time steps, 2000. So 2000, 2005, 10, and 15. Next the next example is related to the infrastructure planning. So I will present to you one of our use cases in Denpasar, Indonesia. So this is the transport network in Denpasar, respectively for 2006 and 2016. So we have three different classes on the map. So the orange class represent arterial roads, or the so-called primary roads. Then we have the yellow class, which is the collector roads or secondary roads. And all other gray lines are represent the local roads. What we are able to do with this transport network. So of course we can do a change layer, and in this case it was a change layer between the two time steps, which are represented with red color on the map on the very right of the slide. Next is another example for delineation of informal settlements. Specifically, the case is Kolkata, India, and this product has been done by another partner, Sears, France, and they did informal settlements mapping in 2017. So this is again a screenshot from a specific area of interest in Kolkata. We use for this screenshot Google Earth. Then you see, so this is the first step of delineating the informal settlements, and you see the polygons of slum areas which are delineated with yellow line. So what we did actually, we combined the information from the delineated features with our land use classification. And you see this, let's call it peach color, is exactly showing to you the informal settlements within this specific area of interest. All other classes, you can see the legend behind. And so this is the overall, this is the overview of the city, and this specific area of interest was from this part of the city. Next, I would like to hand over to my colleague Amelie, who will continue presenting to you other use cases and examples. And then at the end, we'll proceed with our Q&A session. Thank you very much.
Okay, thank you, Daniela. Hello, welcome everyone. My name is Amelie Broszeit, and I will lead you through the second part of the presentation. We start with urban green area planning. And the benefits of having green areas in cities is now an acceptable and important component of urban development and planning programs. EO data was successfully used for the classification of urban green areas and open spaces in Dhaka in Bangladesh. Here in this example, green areas and open spaces were mapped and classified according to 18 classes, like central squares or neighbor squares, or according to different green areas, as you can see on the right side of the map. They are also classified according to its form or location. We now look at a zoom in of this area of the city center of Dhaka and see the detailed mapping of different urban features and also the classification into residential fabric streets, motorways, primary and secondary roads. EO data is also a cost-efficient and quality-assured tool for the assessment of terrain motion, flood and flood risk, as well as landslides over a period of time. Earth observation can provide information about the location, the intensity, and the probable evolution of natural disasters. Thus, these data represent key input into the identification of exposed assets, population, and infrastructure, and the assessment of flood-related risks. This example here shows the extent of land subsidence in Semarang, the capital of Central Java province, between December 2014 up to March 2017. The analysis is based on radar data from Sentinel-1. Everyone who is not familiar with the term land subsidence is the loss of surface elevation due to the removal of subsurface support. In Semarang, land subsidence is a major problem, mainly caused by a combination of natural consolidation of young alluvium soil, groundwater extraction, and the load of buildings and constructions. The land subsidence measured with EO data shows the spatial and temporal variations with maximum rates that go up to, which you can see here, up to over 12 centimeters per year at certain locations. In general, the sensor mapped higher rates of subsidence along the coast and on the right part of the city, which are in higher risk for flooding. For the whole city of Semarang, further on, analyses were conducted and showed, and for this smaller area here, we now look at these analyses. The amount of subsidence in residential areas, for example, or along roads were measured and now highlight areas which are especially exposed to floods or sudden subsidence. The next example shows flood monitoring north of Phnom Penh in Cambodia between December 2015 and February 2017. The flood mapping was also conducted based on multi-temporal Sentinel-1 radar data. The following short animation shows a part of Phnom Penh as well as the mainly agricultural used landscape north of Phnom Penh. The EO data captures very well the large areas which experienced flooding during the incoming monsoon in October and December. And the intense agricultural activities, especially in rice cultivation, support the flood risk and lead to this large extent of flooded areas. Now we are coming to the part covering the Sustainable Development Goals. In September 2015, the United Nations Sustainable Development Summit adopted a set of goals to end poverty, protect the planet, and ensure the prosperity for all as part of a new Sustainable Development Agenda. Each goal has specific targets to be achieved over the next 15 years. The 2030 agenda contains overall 17 Sustainable Development Goals and 169 targets. The SDGs address in an integrated manner the social, economic and environmental dimensions of development, the interrelations, aspects related to peaceful societies and effective institutions, as well as means of implementations. The Goal 11 is the one relating to urban areas and aims to make cities and human settlements inclusive, safe, resilient and sustainable. As I already mentioned, the SDGs are structured into targets which can be measured by different indicators. EO data can support the calculation of some of the SDG indicators, which I like to show below. The indicator 11.1.1 is the one for the proportion of urban population living in slums, informal settlements or inadequate housing. The indicator 11.2.1 it's about the proportion of the population that has convenient access to public transport. The indicator 11.3.1 about the ratio of land consumption rate to population growth rate. Or the indicator 11.7.1, the average share of the built-up area of cities that is open space for public use for all. In the two upcoming slides, I like to show the calculation of these two, which are highlighted on the slide of these two indicators. The first one is the indicator of land use efficiency, which measures and monitors the relationship between land consumption and population growth to enable decision makers to track and manage urban growth at multiple scales in order to promote orderly urban expansion. The ratio of land consumption rate to population growth rate is a good indicator for measuring land use efficiency and is intended to answer the question of whether the remaining undeveloped urban land is being developed at a rate that is less than or greater than the prevailing rate of population growth. I come to it again later when we look at the results. To calculate this indicator, satellite data were used to extract the exact extent in square kilometers of the built-up area, as well as the estimated annual urban population for the reference year of the analysis. A test run was so far conducted for several EU4ST urban cities, namely for Arusha, Dodoma and Kigoma in Tanzania, in Mendoza in Argentina, and in Lima in Peru. The primary aim of urban planning is to achieve optimal land use. A rate of land consumption lower than or equal to the rate of population growth is therefore desired. Only Kigoma and Lima show with a ratio below 1 that the land is efficient used. The next example is the indicator 11.7.1, which calculates the average share of the built-up area of cities that is open space in public use for all. To measure this indicator, the built-up area of the city is again needed, as well as the total area of open public space and the estimation of the land allocated to streets. The built-up area can be directly extracted from satellite data. However, the share of land in public open space cannot be obtained directly by using satellite imagery, as it is not possible to determine the ownership or the use of open spaces by remote sensing. Therefore, additional metadata that helps to describe the land use patterns in the local is required to map out land that is for public and non-public use. The indicator was calculated for 6 cities, again for Arusha, Dodoma and Kigoma, as well as for Semarang in Indonesia, Dhaka in Bangladesh, and Lima in Peru. The analysis was conducted for 2 points in time, a historic one and an actual one. The graphic here shows that Lima and Arusha have the highest amount of open spaces for public use. To wrap up, the value of EO products is defined through verified user requirements to fit user needs, a harmonized and standardized state-of-the-art technology, comprehensive and transparent documentation, the application of sound accuracy assessment, With a very stringent quality control, it is ensured that the applied methodology is transparent, repeatable, complete, and valid. And for all this, user feedback is needed to further improve the services. We are now at the end of this webinar. I hope we could provide you with a small overview over what is possible.
Thank you very much, Amelie, and Daniela as well, for these very interesting presentations.